Let's talk about taking the derivatives of logarithmic functions. First, let's recall some of the things we know about derivatives of exponential functions and some of the things we know about the chain rule. So recall that if you have a exponential function y equal to b to the x, its derivative is simply the same function b to the x times the natural log of b. For example, if you're looking at the function 2 to the x, its derivative would simply be the same function 2 to the x times the natural log of your base 2. Also, recall some of the things we know about the chain rule. So the chain rule says that if you have a function f of x equal to another function h of x composed with g of x, where your h of x is your outermost function and your g of x is your innermost function, you can take the derivative of this composition using the chain rule, where you're going to take the derivative of the outermost function h, evaluate that at g, and then multiply the whole thing times the derivative of g prime of x. If you make a little substitution and say that u is equal to g of x, we can write this line in the following way. F prime of x can be replaced with df of x. The derivative of h evaluated at g of x can be rewritten as dh with respect to u, and our g prime of x can be written as derivative of g with respect to x. Now we'll be using both of these elements to take the derivative of the natural log function. Here we have the natural log base b of x. Now recall that logarithmic functions and exponential functions are inverses of each other, so you can always take an equation written in logarithmic form and translate it into an equation in an exponential form. We can write this as b to the power of y is equal to x. In this equation, we have on the left-hand side a composition of two functions. This is the composition of the function b to the x and the function y. We said that whenever we have the function b to the x, its derivative is going to be b to the x times the natural log of the base b. So the derivative of b to the y is going to be that same function times the natural log of base b. But from the chain rule, we also have to take the derivative of y, and we would end up with a dy dx in the product. On the right-hand side, we simply have x. Its derivative is 1. From this line, if we solve for dy dx, we have that dy dx is equal to 1 over b to the y, natural log of b. And in this formula, we can replace y with the natural log base b of x. So this line turns into 1 over b to the power of log base b of x times the natural log of b. By properties of exponents and logarithms, this term is simply going to be x. So we have 1 over x natural log of b. And just to recap, when taking the derivative with respect to x of log base b of x, that's simply going to be 1 over x times the natural log of b. As a very quick example, suppose we have y equal to log base 2 of x. Its derivative is simply going to be 1 over x times times natural log of 2. Done. Now, we have just said that the derivative of any logarithmic function can be computed this way, but in particular, if b is equal to e, we get a result that's pretty nice. If your b value is equal to e, then when you're considering log base e of x, you're really considering the natural log function. So the derivative of your natural log function, natural log of x, is equal to 1 over x times natural log of your base e, but the natural log of e is simply going to be 1. So this extra little term, the natural log of b, is going to be 1. So the derivative of natural log of x is simply 1 over x.